Hello everyone, today our group, consisting of Keenan, Guan Yu, Akmal, Nicholas and Kim will be explaining the concept of magnetic flux and magnetic induction in the working principle of AC generator.
Now we're going to talk about magnetic flux and magnetic induction. So basically flux is the action or process of flowing, and then we're going to proceed to the concept of flux. So imagine this rectangle box, and then inside the small dots, they basically represent air particles, and then the yellow square represents the surface area, and the blue arrow represents the direction in which air particles travel. So flux in this picture is basically just the flow of air particles through this yellow surface area in a given amount of time. And you realize that this concept of flux is actually applied to magnetic flux as well. So magnetic flux, to define it, it's the number of magnetic field lines passing through a surface area. And the formula here, as you can see, it's phi equals to B, which is the magnetic field strength, times A, which is the surface area, times cosine theta. And theta is the angle that is between the normal line, which is perpendicular to this surface area, and the magnetic field line. We're going to proceed to an example now. So in this first picture, you'll see that there are 5 magnetic field lines passing through this area, and you see that this red arrow is actually representing a normal line, and this normal line is actually parallel to the magnetic field line, meaning that there is no angle between them. So if you were to plug the values inside the formula, you'll get B times A times cosine 0, which will definitely give you a certain value, and a certain value is a flux, and the flux here is actually maximum because the area here is perpendicular to the magnetic field line, meaning that it's actually exposed. It is actually most exposed to the magnetic field lines, and this instead has no magnetic field lines passing through this yellow area, and the normal line is actually 90 degrees to the magnetic field line. Then if you were to plug it into the formula, you actually get a 0 value, meaning that there's no magnetic flux here at all. So now we're going to talk about magnetic induction. Before we start, we're going to talk about Faraday's law. So what is Faraday's law? It's basically Michael Faraday's law, where he wanted to prove that a changing current, a changing magnetic field would induce a current. So he set up an experiment like how this picture shows, and imagine that there's a switch here. So as he closes the switch, the first coil was turned on. He realizes that the galvanometer actually moved. It's because that there's a small current being produced in the second coil. So he proceeded by doing another experiment where he uses a permanent magnet and move it inside and outside and out of the coil. And as he pushes it into the coil, he realizes that there's current being produced. And as he pulls it out of the coil, he also realizes that there's current being produced. But as he held it stationary inside the coil, there's no current being produced. Why? Even though there is magnetic flux when he held it stationary, there's no changing in magnetic flux. Therefore, there's no current being produced. But when you push it in or pull it out, there will be magnetic flux changing. Therefore, current will be produced. And Faraday's law also states that electromagnetic induction, to summarize, is basically the voltage or current that is produced in a conductor, like a wire, because of a change in magnetic flux. So this law of electromagnetic induction says that the induced EMF, which is the electromotive force, is actually directly proportional to the rate of change of magnetic flux in the coil. And d phi here is actually magnetic flux, dt here is time. So divide both of them, you'll get a rate of change of magnetic flux, which is directly proportional to this. And it also states that the amount of induced current is actually proportional to the rate of change of flux. So basically what you do is you just substitute E by I, so that you get the formula of this one. And you also realize that Faraday's law will be applied onto devices such as AC generator, which will be explained later on.
So, what is an AC generator? AC stands for alternating current, and an AC generator is a device that converts mechanical energy to electrical energy and operates on the same fundamental principles of electromagnetic induction as DC generators. Alternating voltage is generated by rotating a coil in the magnetic field or by rotating a magnetic field within a stationary coil. An AC generator is usually made up of 3 main components: which are two magnets with opposite poles, carbon brushes, and slip rings. Now, let's talk about the functions of both the slip rings and the carbon brush. The purpose of slip rings is to allow the transfer of alternating EMF induced in the rotating coil to the external circuit. Each ring is connected to one end of the coil wire and is electrically connected to the external circuit via the conductive carbon brushes. You should also take note of the fact that one of the differences between an AC generator and a DC motor is that a DC motor uses split ring commutator, which reverses the current direction in the coil every half turn and allows the coil to always turn in the clockwise direction. Moving on, electrical current is transmitted from the rotating coil when it comes into contact with a carbon brush. As stated before, the operational principle of an AC generator is based on electromagnetic induction, which is defined by Faraday's law.
Induce a magnetic field going inwards, as you can tell by the poles going from north to south. You can tell a positive current will be produced or an anti-clockwise current, as you can tell by the galvanometer, which is pointing towards the right, which is positive. And you may ask, why is it going anti-clockwise instead of clockwise? Okay, so now let's look at the right-hand thumb rule first. This will be the current, and this will be its magnetic field. As the current is going anti-clockwise, let's follow it. The magnetic field will be going outwards. Outwards, okay? As you can tell, outwards, which is opposing to our initial magnetic field. This is actually because of the law of conservation of energy. We can use Lenz's law to better explain this. By definition, Lenz's law states that an induced current will produce a magnetic field which is opposing to the initial magnetic field. And this is actually why it's moving anti-clockwise instead of clockwise. Okay, so now let's see an example if it actually goes clockwise. If it goes clockwise, using a right-hand thumb rule again, the magnetic field which is opposing to the initial magnetic field, and this is actually why it's moving anti-clockwise instead of clockwise. Okay, so now let's see an example if it actually goes clockwise. If it goes clockwise, using a right-hand thumb rule again, the magnetic field will go inwards, which is following our initial magnetic field. This will not happen because, according to Faraday's law, the magnetic current will be directly proportional to the change in magnetic flux. So if it's going clockwise, the magnetic flux will increase because it's following its initial magnetic field. And as magnetic flux changes more, the strength of the current will increase, which will then increase the strength, which will then increase the change in magnetic flux, and which will then increase the strength, and so on. I hope you understand.
Okay, hey everyone, this is Akmal talking now. Remember when one you talked about flux and electromotive force and how they function? Apparently, you can put that information into a graph, both of which are against time graph. Now, I am here to talk about those two graphs, which are flux time graph and EMF time graphs respectively. And I'll be explaining to you all the relationship between the two. As you can see here, based on Wikipedia, it says that the induced EMF is negatively proportional to the slope of the flux time graph. Thus, the EMF is zero when the flux graph reaches a positive or negative peak. When the flux is decreasing, the flux graph has a negative slope, so the induced EMF is positive, and vice versa. I can see you guys are like, oh my gosh, what is this? And I realize it is very daunting. But I assure you it's very easy. You just need to break the information into parts, into smaller parts. As you can see here, the first part says that the induced EMF is negatively proportional to the slope of the flux time graph. This part just means it's saying that in the graph, when the magnetic flux is increasing, the induced EMF will be negative, and vice versa, which means that when the magnetic flux is decreasing, the EMF produced will be positive. As you can see, it's proven on the graph in the slide below. When the magnetic flux increases, the induced EMF will be negative part, and when the magnetic flux is going down, the induced EMF will be positive, as seen in the graph below, which repeats itself. Alright, let's go to the second part, which is thus the EMF is 0 when the flux graph reaches a positive or negative peak. This means that when there is no change in the magnetic flux, no EMF will be produced, as seen in the graph below. When the magnetic flux reaches a maximum or minimum point, the line in the induced graph won't be a straight horizontal line, it will become a straight vertical line, at which point there is no EMF produced. It starts producing more electromotive force the moment the magnetic flux changes again. The next part shows that when the flux is decreasing, the flux graph has a negative slope, so the induced EMF will be positive, and vice versa. This part isn't very difficult. It's just a repetition of the first part of the definition. It just says that when the flux is decreasing, when the slope is going down, the EMF produced will be positive, and vice versa, as shown there. It's when the flux is increasing in slope, the EMF produced will be negative. Next slide is a picture of a basic flux and EMF graph. If I were to break down this whole graph and show you the relationship between the two, between the flux time graph and the EMF time graph, it would go something like this. It would start with the first increase in flux. When the flux increases, the EMF produced will be negative, as it proves the first part of our definition, which is when the flux has a positive slope, the EMF produced will be negative. Secondly, when the flux reaches a maximum peak, as you can see in the EMF graph, it will have a zero. It will become zero. It will have zero EMF. This is because there is no change in flux, thus no EMF is produced, which proves our second part of our definition correct. And finally, it's just repetition. There's nothing more. That's the only 2 points you need to know about the relationship between the two graphs. It's quite simple, like I said in the earlier part of this video. Thank you for watching and focusing on my voice. Now, on to the next person. Thank you.
So now we're going to talk about how to find EMF in AC generators. So it reads here, if the loop is rotating with constant angular velocity, the induced EMF is sinusoidal. Sinusoidal basically means that it'll create a sine wave, and it looks something like this. Omega is a constant value which can be denoted by 2 pi f, f being frequency. to actually get the magnitude of the velocity, we can use the equation V equals circumference over time. Why is it circumference? Is actually because as the coil is spinning, it will be traveling in circles, and it just basically means its distance over time. This can translate into 2 pi r over t. How it will become 2 pi fr is by this red equation right here on the bottom left. F equals 1 over t. As you substitute that into 2 pi r over t, it will become 2 pi r fr. And if you notice, we can also substitute our omega, which is 2 pi f, into this equation right here, and it will become omega r. Now let's put our focus back to EMF. Looking at this equation, magnetic flux equals to magnetic flux, which is phi, equals to BA cos omega time. And EMF, which is represented by epsilon, is actually basically negative the change in magnetic flux over the change in time, which will, and then if you do differentiation, if you differentiate this equation right here, you'll get BA omega sine omega t. This equation is actually just assuming that you have one loop of wire. If you have more than one loop of wire, you can multiply the equation by n. N being the amount of loops. Okay, so this equation right here written as maximum of EMF, which is epsilon naught sine omega t. You can actually get this by looking at the graph. At its highest point, sine will be 90 degrees for sine graph, and if you sub 90 degrees into this omega t right here, 90 degrees basically means it is the core of wire is perpendicular to the magnetic field, and if you sub 90 degrees into omega t right here, you will get NBA omega multiplied by 1. And this is basically the equations that you will need to calculate EMF for AC generators.
I am going to talk about the production of back EMF in motors. As the term back electromotive force is also commonly used to refer to the voltage that basically occurs in electric motors, where there is relative motion between the armature and the magnetic field that produced by the motor's field coils, thus also acting as a generator while running as a motor. This effect is not due to the motor's inductance, but a separate phenomenon when the armature of DC motor rotates under the influence of driving torque. The armature conductors move through the magnetic field, and hence EMF is induced in them as in a generator. Those induced EMF acts in opposite direction to the applied voltage V and is known as back or counter EMF. Example of back EMF in motors. An armature winding having a resistance of 5 ohms and connected to a 120 watt source. When the motor reaches full speed under normal load, the back EMF is 108 watts. As a formula shows that the startup current is I equal to V over R equal to 120 watts over 5 ohms will be equal to 24 current. And the running current is 120 watts minus 108 watts, and you will find out that it will be equal to 5 ohms, and using the 5 ohms to find the current, it will be 12 watts over 5 ohms, and it will be equal to 2.4 current. And basically that's all I want to talk about the production of back EMF in motors. Thank you.